Howdy, junior microbiologists. Welcome to chapter 17. So this chart kind of shows where we are. So we're talking about immunity, and in chapter 15 we did innate immunity. That's also called non-specific immunity. And chapter 15, innate or non-specific immunity, had two sub-arms. The first line of defense and the second line of defense. And then chapter 16 was adaptive immunity, aka specific immunity, and adaptive or specific immunity included the third line of defense, and adaptive immunity was chapter 16. So now we're in chapter 17, immunization. So I'm sure you've all heard of immunization, and maybe you've had some immunizations, but this is a continuation of adaptive immunity. So there's a natural immunization and artificial immunization. And in natural immunization, you have passive and active. And within artificial immunization, you also have passive and active. So you could say you have natural passive immunization and natural active immunization. And you can have artificial passive immunization and artificial active immunization. So let's look at a brief history of immunization. This was actually on, there was a little PBS thing on this woman, NPR, Lady Mary Wortley Montagu. And she plays a kind of a non-scientific role in immunization. So in the 12th century in China, the Chinese people, Chinese parents, if they had a child or children that they knew who had survived a very mild case of smallpox, they would take the smallpox scabs from those children, they would grind them up into a really fine powder, and then they would I'm not really sure how they did it, but they must have taken needles and gotten the powder on the tip of the needles maybe and poked their kids with it. So basically, and they called it variolation. And it really did significantly decrease the overall morbidity and mortality of smallpox. And then in 1721, this concept of variolation spread to the Ottoman Empire, and this lady, Mary Wortley Montagu, was the wife of an English ambassador to the Ottoman Empire. She did this to her children, and everybody, well, a lot of people thought it was cool, and they used it when they heard about it in England. They used it in England, and then they heard about it in America. Many people survived this severe form of smallpox with this technique, but 1 to 2% of the recipients would die. So they said that powers that be said we're gonna outlaw this. And of interest, variola is the virus that causes smallpox, and it's a member of this orthopoxvirus genus. Okay, so here's a painting of Edward Jenner vaccinating, doing one of the first, I guess, technical vaccinations. And there's a lot of different stories about who he vaccinated. Some stories I've heard he just got some kid from the community vaccinated him. Some I've heard it was his maid's kid, so this could be her kid. But anyway, I don't know what the true story is, but he got a kid, and what he did is he knew that these milkmaids, I guess that's what they were called in the old days, they milked the cows, and they would get this disease called cowpox, and it didn't kill people. And he noticed that these milkmaids that got cowpox never died from smallpox. So he thought, wow. He thought that he could protect people from this really deadly and horrible disease of smallpox with crusts from scabs from people with cowpox. And so he did it, and he called it vaccination, from vaca, which is Latin for cow, and vaccinia is Latin for cowpox, and so that's where we get vaccination. And then in 1879, Louis Pasteur demonstrated he could make an effective vaccine to the fowl cholera causative agent. And then Pasteur made vaccines against rabies and anthrax. And then he found out he could transfer antibodies to susceptible individuals to protect them, and that's passive immunotherapy. And we'll talk about that later. So here's a table from your book, The Principal Vaccines to Prevent Human Disease. So in this first column is the vaccine recommended by the CDC. So for example, the vaccine is called the hepatitis B vaccine. The disease agent is the hepatitis B virus, and the disease is called hepatitis B. The vaccine here is called rotavirus. The disease agent is rotavirus, and the disease is gastroenteritis. So you can look through this. I think a lot of you are working in the clinic already, and you've probably had this shot, this vaccine called DTaP, to protect you against all the diseases in the hospitals. So by the 1900s, vaccines became available against polio, measles, mumps, rubella. And in the present, we have a lot of vaccines, including vaccines against chickenpox, Hep A, Hep B, organisms that cause influenza and pneumonia. And as you know, the scientists are working tirelessly to make a vaccine against the coronavirus. So these graphs, let's look at the y-axis. It says number of cases in the thousands. So it would be 10,000 up to 50,000. And then it shows the year, and then it tells you the disease, and then when the vaccine came in. So here's polio. I think it's from the United States, but it could be worldwide. But anyway, here's the number of cases, 40,000 cases. And then you introduce the vaccine here in, I don't know if that is, maybe 1956, you introduced the vaccine, and look what happens to the number of cases. And then it goes up a little bit, and then you introduce another vaccine, and now it's pretty much flatline for polio. Same thing for rubella, where you introduce the vaccine, the number of cases go down. Measles, the number of cases go down, and mumps, the number of cases go down. In developing nations, over 3 million children worldwide still die from vaccine-preventable diseases. There are vaccine-associated risks, but it's a very low risk, and it's a very great reward because you get to live. Okay, let's take a look at this table. It's a comparison of the types of acquired immunity. So, and they call it, you can call it different things. So if you look here in this first column, these would be active immunity in this column, and then the second column would be passive immunity, and in the first row would be naturally acquired, and in the second row would be artificially acquired. So check out this little guy. This guy, probably chickenpox, he's acquiring natural active immunity, or some people call it active naturally acquired immunity. So he was infected with the virus, and then his own body made antibodies, and so he ran the course of the disease, and his immune system, his antibodies, staved off the disease. In artificially acquired immunity, it's also called artificial active immunity or active artificially acquired immunity. This is where you get a vaccine. So artificial active immunity, aka active artificially acquired immunity, is the whole concept of a vaccination. Now we come over here to the second column. There's passive acquired immunity. So you could have natural passive immunity. That's when the antibodies are transferred from the mother to the offspring. That's also called passive naturally acquired. So obviously the natural part is you're naturally, the mother naturally makes it, and the baby is getting it passively. The baby's not making it itself, but it's acquiring it passively. And then this last square in our table, this is in the passive column and the artificially acquired in the artificially acquired row. So this is artificial passive immunity or passive artificially acquired immunity. So it's passive because this person getting the shot is not making the antibodies. She's acquiring them artificially. So when you get anti-sera or an antitoxin, some kind of preformed antibody in a shot, that's artificial passive immunity. Okay. When you have naturally acquired active immunity, that means you did get ill and you use your own immune system to recover from the infection. Down here again, we said this is vaccine. You get a vaccine, and then hopefully you don't get ill. In this photograph, the example is breastfeeding, where the baby gets the natural passive immunity. And so, for example, if you remember from B cells, we talked about this antibody, aka immunoglobulin, IgG. It can cross the blood placental barrier, and it's important for natural passive immunity when you are a fetus and you're living in the placental world. You can get IgG from your mother. And then this is interesting because they've kind of been talking about this with COVID-19. If someone who was previously ill from your disease of interest, like COVID-19, and you get their blood, they've got the antibodies in it, and you give that blood transfusion to someone else, that would be an example of artificial passive immunity. Okay, so naturally acquired active immunity, the body responds to pathogens, so viruses or bacteria, and other environmental antigens. So remember, this is a little tricky. The pathogens, the virus, so the pathogens can be virus or bacteria, and they're covered in proteins, and those technically are the antigens and epitopes. So it just says here, body responds to pathogens and other environmental antigens, could be a free-floating toxin, by mounting a specific immune response. So you get sick with the disease, but your body naturally is engaged in its own protection. Naturally acquired passive immunity, embryos or fetuses and newborns get preformed antibodies from mom. And we just talked about this. The placenta can deliver IgG to the fetus. Mother's milk can deliver IgA, because the child does not actively produce its own antibodies yet. So artificial passive immunity is a medical intervention. So you can harvest antibodies from immune animals. So you can inject the animals with your antigen of interest, and those animals can make antibodies against it. And then you can harvest those antibodies, and then you can put that into a injection. So, and that would give the patient immediate protection. So, for example, rabies, you need immediate protection, you need artificial passive immunity. And you could just give, you could harvest the antibodies, or you could just give the anti-sera. That's the liquid portion of the blood with the antibodies in it, or antitoxins in it. Artificial passive immunity involves the administration of antibodies, so we talked about that. It's immediate protection. Traditionally, we got these antibodies for artificial passive immunity from human or animal donors that had the disease and then were actively immunized against it. But now we can make more antibodies, higher amount of antibodies using cell lines. So artificial passive immunity is also called passive immunotherapy. So you use passive immunotherapy when you need help immediately. And if the anti-sera, remember that's the liquid portion of the blood that has the antibody in it, anti-sera, so serum, against toxins is called an antitoxin. So for example, if you get infected with tetanus, you would need an injection of anti-sera containing antitoxin specifically against tetanus toxin. Oh, and since we all live, well, maybe everyone's taking this class doesn't live in the Southwest, or in the West, snake venom. So anti-sera, so that's liquid portion of the blood with the antibodies against the snake venom, is called anti-venom. So we have anti-sera, and then the different types of anti-sera, antitoxins, antivenoms. And here's just a photograph of rabies anti-serum. Infections with certain viruses are treated with anti-sera directed against that specific virus. So all of these guys are viral diseases. So if you have been exposed to rabies and you get both human rabies antibodies injected near the bite site, and you get the rabies vaccine, so you're getting 2 injections. This strategy is called active immunization combined with passive immunotherapy. So active immunization means you're giving the vaccine against rabies, but you're also giving the antibodies immediately against rabies so that you don't die. Okay, it's for artificially acquired passive immunity. So this is what I was telling you, you could make cell lines that make antibodies against your antigen of interest. So in this cartoon, it shows you we use a mouse and we inject it with the antigen, the toxic or the pathogenic antigen of interest. And then the mouse has B cells that will make plasma cells that will make antibodies. So now you have these plasma cells here that make the antibodies. And then over on this side, you have a flask of long-lived myeloma cell lines grown in culture. And you put these 2 cell types together, and then they form this hybridoma that these cells live for a really long time and continue to make these antibodies of interest for you. And so that's kind of a good deal. Way to go, science. But this is a monoclonal antibody. It can create a continuously dividing cell that secretes one type of antibody, your antibody of interest.